Assistant Professor in Chemistry, Nirmala College for Women, Coimbatore. Solid state chemistry deals with structure, synthesis and properties of solid phase materials. Crystal in solid state is determined by three-dimensional periodic arrangement of atoms or ions or molecules in space. Ideally, they should be perfect order in this arrangement. As per the law of nature, nothing is perfect, and so crystals need not to be perfect. They always have some defects in the arrangement of their constituents. These defects affect the physical and chemical properties of the solid and also play an important role in various processes. For example, a process called doping leads to a crystal imperfection and increases the electrical conductivity of a semiconductor material such as silicon. The ability of ferromagnetic material such as iron, nickel, etc. to be magnetized and demagnetized depends on the presence of imperfections. Crystal defects are classified into four types. They are point defects, line defects, interfacial defects and volume defects. In this module, we concentrate on point defects, more specifically in the ionic solid. Any deviations from the perfectly ordered atoms or ions or molecules in crystals is called imperfection. Point defect can be defined as irregularity or deviation from ideal arrangement in the entire row of lattice point. It is classified into three types: stoichiometric defects, impurity defects and non-stoichiometric defects. Stoichiometric defects are classified into Scorched defect and Frenkel defect. Non-stoichiometric defects are classified into metal excess defect and metal deficiency defects. Point defects are produced in an ionic crystal when an equal number of cations and anions are missing from their regular lattice position. It may be in stoichiometric as well as in non-stoichiometric crystals. The defects found in stoichiometric ionic crystals are called stoichiometric defects. It is classified into two types: Scorched defect and Frenkel defect. First, we will start from Scorched defect. Scorched defect is created in the crystal when the same number of cations and anions are missing from their positions and thus holes are produced. Since the number of cations and anions that are left in the crystal even after the missing of cations and anions is the same, the crystal remains electrically neutral. But we consider the density of an ionic crystal having Scorched defect, it decreases. This is because of the missing of cations and anions. Generally, this defect occurs in highly ionic crystals having high coordination numbers and the equal size of cations and anions. For example, sodium chloride crystal. In sodium chloride, 1 Na plus and 1 Cl minus ions are missing. So it results Scorched defect. Potassium chloride, potassium bromide and cesium chloride are other examples. Frenkel defect. It is created in the crystal when an ion, it may be cation or anion, is missing from its lattice position and occupies the vacant interstitial site existing between the cations and anions. Since the number of cations and anions remain same, there is no change in the density of the crystal having Frenkel defect. Generally, it is found in those ionic crystals which have low coordination number and the size of the cation is smaller than the anion size. Example, zinc sulfide, silver chloride, silver bromide and silver iodide. In silver bromide crystal, 2 silver plus ions are missing from its lattice position and occupies the vacant interstitial site. Non-stoichiometric defect. Depending on whether the positive or negative ions are present in excess in a given non-stoichiometric crystals. There are two types. First one is metal excess defect, another one is metal deficient defect. Metal excess defect may be produced by two reasons. One is missing of one or more anions or the presence of extra one or more cations in the interstitial site. In the first case, due to the missing of anions, vacancies are produced. In order to maintain the electrical neutrality, it is occupied by the electrons since it carries negative charge. The electrons which occupy the anion vacancy are called F centers or colored centers. For example, we consider sodium chloride. One Cl- is missing, so it is occupied with electrons. If we consider the second type, when one or more cations occupy the interstitial site, and in order to maintain the electrical neutrality of the crystal, equal number of electrons are trapped into other interstitial site. For example, zinc oxide, it loses oxygen reversibly at high temperature and becomes yellow color. The excess of zinc 2+ ions are trapped into the interstitial sites, and equal number of electrons also trapped into other interstitial site to balance the electrical charge. In metal excess defect, the number of electrons is low. The crystals show low electrical conductivity and are called as N-type semiconductors and are generally colored. Metal deficient defect, it is produced when one or more cations are missing from the positions and created cation vacancies. In order to maintain electrical neutrality of the crystal, one or more nearby cations acquire extra positive charge and are thus converted into cation with higher oxidation state. For example, iron oxide, nickel oxide and ferrous sulfide. In the crystal of ferrous oxide, one Fe2+ ion is missing and two Fe2+ ions acquire one extra positive charge and become Fe3+, so that the electrical neutrality of the oxide crystal may be maintained. In metal deficient defect, movement of a cation is also called movement of a positive hole, and thus the substance are called P-type semiconductors. The third type is impurity defect. It is created by addition of impurities. For example, addition of cadmium chloride to silver chloride yields solid solution where the divalent cation cadmium 2+ occupies the position of silver+. This will disturb the electrical neutrality of the crystal. In order to maintain the same, proportional number of silver+ ion leaves the lattice. This produces a cation vacancy in the lattice. Such kind of crystal defects are called impurity defects. Other example, addition of strontium chloride to sodium chloride. In this case also, strontium 2+ occupies the position of Na+. Then Na+ ion leaves the lattice and it produces cation vacancy. Finally, we conclude, crystals always found to have some defects in the arrangement of their constituent particles. Scorched defect arises due to the missing of equal number of cations and anions. Frenkel defect arises due to dislocation of ions from its crystal lattice. Metal excess defect arises due to the presence of more number of metal ions compared to anions. Metal deficiency defect arises due to the presence of less number of cations than the anions. So in this module, we learnt about imperfections in solids. Thank you for watching this video. Happy learning.